Okay, we're going to pick back up here. It looks like they found a bulb, so that's good. All right. So we're off to chapter 12, I think, and chapter 12, we're going to deal with a bunch of other organic groups, including alcohols, ethers, I believe, thiols, aldehydes, and ketones. So we're going to actually start a little bit ahead in the notes. We're going to actually start with the aldehydes and ketones, and then we'll go back to the earlier part of the notes. So we're going to pick up right around here in terms of the notes. Like I said, we'll go back after we talk about this because I think this is relevant to this week's labs, if I'm not mistaken. So the next two sort of organic groups we're going to talk about are aldehydes and ketones. And aldehydes have the functional group of a carbon-oxygen double bond to a hydrogen. And the ketones functional group is basically a 3-carbon run with the carbon-oxygen double bond in the center of that 3-carbon run. So the simplest ketones, known as acetone or propanone, is a colorless liquid with a mild odor. It's kind of like your nail polish remover everybody loves to open in a closed car. And that is the simplest one you could have because you need 3 carbons in a row to have a ketone. So a couple important things about these groups in terms of their location. First off, the aldehyde group there will always be at the end, and the aldehyde group will always find itself at the end because of this hydrogen. And as we know, hydrogen could obviously only have 1 bond, no more than 2 electrons. So you can never have that functional group inside or away from the ends. Otherwise, the hydrogen will have too many bonds. Opposite of that there is the ketone, because you need sort of the 3-carbon run on it. Frankly, that double bonded carbon oxygen should never be at the end because you need 3 carbons in a row to do that. So you'll kind of never find the ketone group, or at least the carbon oxygen double bond part of it, at the end of a molecule. But you should always find the aldehyde group at one end of the molecule or the other because of that hydrogen. Now, both of these guys have what I refer to sometimes as a carbonyl group, and a carbonyl group is that carbon-oxygen double bond. That's the carbon and oxygen double bond, and that is a polar sort of group. The carbon being less electronegative than the oxygen, so the oxygen being really more negative in that case, carbon here being more positive. And it does create some ability of these sort of groups here to interact well with maybe some other things that are also polar through that group. They consist of the carbon-oxygen polar double bond, has 2 lone pairs. Again, in a lot of cases in organic, we sometimes don't really draw the lone pairs a lot of times, but they are there, and they are there in both of those cases in a ketone, which is this guy's functional group, and again, also in the aldehyde as well. So the aldehyde is attached in to the carbon with at least 1 hydrogen, and our ketone has, again, some alkyl groups that are attached to it. So once again, this is our functional group right there for our aldehyde, and this is our functional group, whoops, and that guy as well, for our ketone. Actually, that entire thing, basically, as we look at it. Now, if we were to draw some of these in sort of line structures, we really do the same thing, except that, you know, at the end, we would do maybe something like this for a ketone. We would also perhaps do something like this for a ketone, and I'm sorry, an aldehyde here at the end. It would look something like that at one end or the other. And again, here you'll see your groups in line structure form. That's our carbon. That is 2 bonds to the carbon and 1 more coming in there, which means, again, not drawn is our hydrogen that should be there at the end, which will give you your aldehyde functional group. This is our 1 carbon, 2 carbon, 3 carbon run, obviously with our double bond there, which makes the ketone sort of group. Now, when we go to name these guys, we still fall back to, as we've been talking about, really the first 10 alkene names, and it is based on the longest continuous carbon chain that obviously here will contain the functional group, either the aldehyde functional group or the ketone functional group does need to be part of it. So our aldehydes here can be written a couple different ways. You might see it in sort of condensed formula written like that, CHO, and that does imply that you have basically this group. Sometimes CO is written, which implies it is the carbon-oxygen double bond that is there. By the way, if we did have a ring type structure that was a ketone, it would look something like that, for example. And again, that is a carbon, carbon, carbon with our double bond there that gives it the ketone group. Now, if we had something that maybe has an aldehyde group, you typically will actually see more of the aldehyde group sort of attached to the ring like that. Again, otherwise we're going to run into some trouble with that hydrogen at the end of that group having too many bonds. So we definitely could have sort of cyclo guys of these guys or ring type structures of these guys as well. So let's talk about naming aldehydes first. So when we name aldehydes, again, it is the longest carbon chain. With obviously our aldehyde group as part of it. We then will name anything else that's attached to that longest carbon chain, just like normal as groups. We will number the chain, and always when we number the chain, when we're dealing with aldehydes, that is carbon number 1, always. So no matter which side that functional group ends at, that should always be carbon number 1. Then obviously, if there's anything else attached, they are named or numbered accordingly. Now, we do not, unlike alcohols, double bonds, triple bonds, we do not need to incorporate a number into the name for that carbonyl group there in the aldehyde case, because it is always carbon number 1 and it's at one end of the molecule or the other. So it's always sort of there. So you do not need to say like 1, whatever it may be. Now, how we name it is pretty much we drop the E and we put AL at the end of the name. So the IUPAC name, for example, of this guy right here, this has 1 carbon, which is based off of methane. That is our functional group. So this is methanal, AL at the end of it. We had this guy here. This is 2 carbons, which is based off of ethane. We have our functional group right there. That's going to be ethanal, AL, at the end of it. So again, here we use AL at the end. We want to make sure longest carbon chain. And again, in each of these cases, obviously, this would be carbon number 1 if we needed to number anything along the way. There's only 1 carbon here, obviously, so that is carbon number 1. There is some common names, and we won't use too much of the common names here, but 1 carbon, which is this one, methanal, it's also everybody's favorite formaldehyde. And perhaps if you've taken biology or seen formaldehyde or smelt it, you would remember it. So that is formaldehyde. Acetaldehyde is ethanal, propanal, and so forth as we go through it. So if we had something like, say, this guy here. Take a moment there and come up with the name here. All right, let's take a look. So we're gonna go longest carbon chain. So that is 1, 2, 3, 4, 5. Your other option would be 1, 2, 3, and only 4, which obviously is not the longest there. Remember that it does need to contain the functional group there. So it does in this case. So that is 1, 2, 3, 4, 5. That's based off of pentane. We have our aldehyde group here. So this now becomes pentanal, Al, at the end of it. We actually do have a group that's attached here as well, and that would be our 1 carbon group, which is our methyl group. So in this case, we are forced to number appropriately. And again, wherever this carbonyl group is always going to be carbon number 1. This would be carbon 2, this would be carbon 3, carbon 4, and carbon 5. That means that our methyl group there is sitting at carbon number 3. So this should be 3-methyl pentanal. Question on that one there. So very similar to everything else we did, longest carbon chain, including the group, that double bond there, carbon, oxygen double bond, always carbon number 1 in this particular case. And we then obviously name our groups like normal. We give the location. We have multiple groups, then obviously multiple numbers, right? And locations, alphabetical order, just like everything else that we've done. Any questions on that there? All right. So as we can see here, looking at these guys, this is our methanol. It has 1 carbon. This is our ethanol, which has 2 carbons. 1, 2, 3 are propanol, and obviously 1, 2, 3, and 4 are butanol, again named after butane, obviously here. All right, so why don't you do that one? Let me do a few more here. Let's do why don't you draw? Let's do 2-propyl. Hexanal. But you also give let's do to 2 2-butyl 3-methyl. We'll do pentanal. Yeah. All right. So draw those 2 and give the name of the other ones. See what you come up with. I will too. I just made it up. We'll hope for the best here. So, okay, let's take a look, see how you're doing. We'll start top right here. Longest carbon chain. Again, it does need to contain obviously our aldehyde group here. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. I think that's going to be a winner in terms of the longest carbon chain. We also obviously have a methyl group there as well. So starting with the sort of base of our name here, 1, 2, 3, 4, 5, that is based off of pentane. So that's going to be pentanal, Al, at the end of it. This will definitely be carbon number 1, which means at carbon number 2 is our methyl group. So that should be a 2-methyl pentanal. Any questions on that one? Coming over to the one I just started drawing randomly here. This is our functional group right here. Again, there's a carbon there and an H coming out there that is not obviously drawn. So in terms of carbons, our longest carbon chain. Oops, and I just erased. Let's do that. There we go. All right, so our longest carbon chain in this particular case, starting at the carbonyl carbon, we got 1, 2, 3, 4, 5, 6, and 7. I think you could also get 7 if you detoured down this way and went up over. That would give you 1, 2, 3, 4, 5, 6, and 7 if you went kind of that way, if you chose to do that. So it does look like 7 is a winner here, no matter which way you go. In terms of groups, we then have a couple of groups kind of hanging off of here. This is just a 1 carbon group, and this is a 1, 2 carbon group happening there. So that is going to be an ethyl group, and that will be a methyl group. So remember, a line with nothing at the end of it is a carbon with 3 hydrogens, or a methyl group. So 1, 2, 3, 4, 5, 6, 7. That was your news update. This is heptanal here. So this is going to be carbon number 1. Again, we got an always number where the functional group is carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6, and carbon number 7. So we do have obviously here then a 3-methyl. This would be a 5-ethyl. We still go alphabetical regardless of number. So that's going to be a 5-ethyl dash 3-methyl, and we'll join them up together there, heptanal. Any questions on that one there? All right, then we're going to do some drawing here. And as we've talked about previously, we always want to work backwards here. So Al tells us it's an aldehyde group, and hexane or hexanal is basically 6 carbons. So that's going to go with the 6 carbons to start with. 1, 2, 3, 4, 5, and 6. Now, because you're drawing it, we can put our aldehyde group on the left-hand side, right-hand side. It doesn't really matter. I'm going to go right-hand side. Why not? We'll put it there. Now, because I did put it on the right-hand side, for me, that would definitely make that carbon number 1. If you put it on the other side, then your carbon number 1 would be on the other side of the molecule. Now that takes care of that name. That means at number 2, I have a propyl group, and I'm just going to go up and away. Propyl is 3 carbons, right? And now everything else here should be hydrogen. So we need a couple there, couple there, couple there, couple there, and 3 there. And we can do the same thing for our group. It needs a couple, and 3. Any questions on any of that? That obviously is the condensed formula there. Yes, that's true. Questions on that one? All right, do the same thing here for this one. We got pentanal. So I think maybe I'll just go right here. 1, 2, 3, 4, and 5. Once again, Al at the end of it tells us it's an aldehyde, so you can put it on any side you like. So I'll go this side this time. Because I chose to put it over there, that will then make that carbon number 1 for me. And at carbon number 3, I have a methyl group. So it's 1, 2, 3, and a methyl group would just be a CH3. And at carbon number 2, I have a butyl group, and that's based off of butane, which is 4 carbons. 1, 2, 3, and 4. And pretty much everybody else here going to be hydrogens. Remember to get carbon to 4 bonds. That's how we know how many hydrogens we should put there. And we don't want to put extra ones. I can get rid of the number here so it don't look like anything. There we go. And we also need to clean up the bottom there. So we need a couple there, couple there, couple there, and 3 there. Any questions on that particular one there? Question on how to name aldehydes, draw aldehydes. So aldehyde is not too bad. Again, pretty much always carbon number 1, wherever that functional group is, all our groups named accordingly. So let's talk then about how to go about naming ketones. They are a little bit different in terms of how we name ketones. So let's talk about that. When we name ketones, we basically drop the E and put ONE at the end of it. So the simplest ketone you could have, because you need a 3-carbon run, is this guy here, which has 3 carbons. So 3 carbons is based off of propane. Drop the last part there, and it becomes propanone. O-N-E. Now, unlike aldehydes, when you get to about 4 or more sort of carbons, there are multiple locations where technically you could put the carbon-oxygen double bond. So you do need to start giving the numbering, kind of like what we did with double bonds, triple bonds. When you get 4-ish, 5 carbons, you do have to incorporate that into the name. Here you don't, because frankly, there's only one place it could go. It's got to go in the center, because there's only 3 carbons total, and you need 3 carbons in a row to make a ketone along with that double bond. So here, this is our 4 carbons, but really about 5, you should start doing it. Some people will do it for 4, but this is basically butanone. And the really reason you don't need it is because if it was over here, it would still be the same numbering. So starting at number 5 carbons here, we have 1, 2, 3, 4, 5, which is pentanone. Location of the carbon oxygen double bond, or the carbonyl group, is at carbon number 3. The reason you need to do that is if you had this instead, now our carbon oxygen double bond is at which carbon? Carbon number 2. So this would be 2 pentanone. So there are different options as to where it could go. So you got to let people know kind of where it's at when you do have that. This is cyclohexane, this particular guy here. And this is the functional group. That is our group sitting right there, oftentimes missed. And becomes the ring, and that's the functional group. That has to be carbon number 1, which means if we go clockwise, it will put our methyl group at carbon number 3 if we number it, and that would be 3-methyl cyclohexanone. So 5 or more carbons, you really should put the number as to where the carbon oxygen double bond is located. You want to obviously give it the smallest number. So whichever way will give that carbon oxygen double bond the smallest number. Once you lock that in, it kind of takes the priority, and then every other group that may be there is numbered accordingly based off of it. All right, so why don't you name that one there? Do that one. Let's do belly. Once you name those 3, and why don't you draw? Let's do 2-methyl cyclopentanone, and let's do 3-ethyl or hexanone. Okay, let's take a look, see how you're doing. We'll start here with the original one, and we do not want to forget the carbon here. That's 1, 2, 3, 4. You could go down to 5, or you could go straight across to 5. So it does look like 5 is the most. Remember that it does need to contain that ketone group in this case. And by the way, that ketone group is right here, is the ketone group sitting right there. So that is 1, 2, 3, 4, 5. So that's going to be based off of pentane. So it's going to be a pentanone. We do need to give the location here of the carbon oxygen double bond because it's 5 or more. And we want to give it the smallest number. So going right to left here should accomplish that for us. So that means that this is going to be 2-pentanone. And because we have to lock the numbering in based off of the functional group, that means our one group that's hanging out there is going to be at carbon number 4. And that would give us a 4-methyl 2-pentanone. Any questions on that one there? Going to the line structure, we're going to take, so you can go at the end here, 1, 2, 3, 4, 5, 6, and 7. I think that is a winner. You could also, I believe, start up here and come down and also get 7 if you go down and to the right. But I believe 7 is the longest, so we'll go with the straightest one there. By the way, in case you cannot see it, this is our ketone group right here, carbon, 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 with obviously our double bond in the middle there. And that means that we do have a couple groups hanging off there, a methyl group there, and a methyl group hanging out right there. So that's going to give us a little dimethyl action happening there, right? Feels like principal now. I cannot download it. All right. So this is going to be our dimethyl that's happening here. And we do need to give the location where that's at, but we also need to remember how many carbons that was. Was that 7? 1, 2, 3, 4, 5, 6, 7. So that's going to be heptanone, O-N-E, because it's a ketone. And we do want to give the carbon oxygen double bond the smallest number. In this case, doesn't make a difference for the carbon oxygen double bond which way you go. It does not. It's going to end up at carbon number 4, I believe, no matter which way you go. 1, 2, 3, 4, 5, 6, and 7. Or if you went the other way, 1, 2, 3, 4, 5, 6, and 7. Which way should I number in this case, you think? Yeah, so since it doesn't matter in terms of the functional group here, the next sort of priority would be the groups that are attached, which would be the methyls. So we probably would want to go with the blue way there to give us our methyl groups a smaller number. Again, it doesn't make a difference for your ketone group, but it does make a difference here. So we will go that way in terms of numbering. That means still, though, our functional group there is not a 2. It's like a 4 if I wrote 4. Let's try that again. There we go. So it is at 4 heptanone. And because I did go that way, that would be a 2, 3. I'll try to squeeze it in here. Dimethyl dash 4 heptanone. Yes. Any questions on that one there? Coming here, this entire thing here is our longest carbon chain, and that is a cycloalkane, and that is cyclopropane, but it does have our ketone group, so this is going to be cyclopropanone. Cyclopropanone. Again, the ketone group sitting right here, carbon, carbon, and carbon with our double bond happening right there. Any questions on any of those names there? All right, then let's draw our picture here and go with cyclopentanone. O-N-E tells me it's a ketone. Cyclopentane tells me it's really a 5-member ring happening here. And I'm just going to draw more line structure. I really could lay up my carbon oxygen double bond at any of these spots there along the ring. I'm just going to go straight up with it, but it really doesn't matter where you kind of put it. You can put it at any of them. What does matter is wherever you put it, that's going to be carbon number 1. So that's the important part. And that means that at carbon number 2, which would either go left or right in this case, we would have a methyl group that looks something like that there. Any questions on that? And lastly, we have hexanone. So I'm going to go this way. 1, 2, 3, 4, 5, 6. ONE tells us it's a ketone group, and the 4 tells us it's at carbon number 4. So again, you're drawing it. You could go either way. I'm going to go left to right. So for me, I'm going to call this carbon number 1, which means that carbon number 4 is where my really ketone group should be, or my carbonyl carbon. And because I chose to go in that direction, for me, that means that this right here would be carbon number 3, and that is where my ethyl group would be. Which is a 2-carbon group. And again, everybody else here is going to be hydrogens in this case. To get everybody to the proper number, we'll steal that there. Yeah, carbon to 4 bonds. Any questions on ketones, how to name them, how to draw them? All right, then let's talk a little bit about some properties here of aldehydes and ketones. So aldehydes and ketones in water, they can form hydrogen bonds with water. They cannot hydrogen bond with themselves because they frankly don't have a hydrogen that's attached to a carbon, oxygen, or nitrogen, oxygen, or fluorine, I guess. But they can hydrogen bond with water through the carbonyl group. So remember, as we saw earlier, that carbonyl group is partially positive there on the carbon, partially negative on the oxygen. So when water, which is a polar molecule, is negatively charged on the oxygen, positively charged on the hydrogen, they could do some hydrogen bonding here. So they're able to hydrogen bond with water, which means that they are going to be soluble in water. Now, they are going to be soluble in water when they're not so big. So like 4 or less sort of carbons, and they will be able to be soluble in water. As you increase the number of carbons, everybody gets in the way of water being able to kind of get in there and interact well with it. And you have a much bigger nonpolar part that will be insoluble in water. So about 4 or less carbons, and you're usually pretty good in terms of solubility. About 5 or more carbons, then pretty much not going to be very soluble in water because it will not be able to interact well with water. So that's what we see here. Basically up to about 4 carbons for both our aldehyde and our ketones as well are pretty soluble. But once you start getting into that 5, you're really starting to diminish some of that solubility. And pretty much at 6 or so for both of them, you're not going to get much. Again, what happens as it gets bigger, you really only have this small little part that can interact with water. But as this thing gets bigger with lots of carbons, again, sometimes referred to as steric hindrance, like things get in the way and it's just the water can't get in there enough to make it really soluble. So 4 or less, you're good. 5, you're kind of pushing it. 6, you're pretty much out of luck in terms of solubility of aldehydes or ketones with water. Any questions on that there? Yeah. So important aldehydes and ketones. It is a acetone, which is propanone. It's, like I said, nail polish remover, also a solvent used for formaldehyde, right, to preserve some things, which is methanol. So again, these 2 names you should know, methanol and formaldehyde, are really the same thing. People still obviously use formaldehyde in terms of the name very commonly. Acetone as well, and propanone also sometimes used a lot. Still, acetone is used a lot still as a name. Important aldehydes and ketones. Here we have benzaldehyde, which is like an almond type of flavoring. Vanilla, as you can see, these are our aldehyde groups here. And this is cinnamon, basically, which is our ketone group right about there happening there. So these guys obviously play some roles into some of these names. As you can see, as I was mentioning earlier, typically in a ring type structure aromatic with benzene, you will see that sort of whole aldehyde group sort of attached off of the ring. Unlike when we have that ring structure where, you kind of incorporate the ketone into it there with the aromatic there, you'll definitely get that aldehyde group kind of attached separately from it. All right, classify each of these as aldehydes or ketones, and why don't you give the names as well? So take a moment and do both of those. Okay, let's take a look here. Let's first identify each of these here. So starting the first one, we have a 3-carbon run and a double bond. So that is a ketone. We have our basically carbon, oxygen, double bond, and hydrogen, which would be an aldehyde. Also, same thing here, our carbon, oxygen, double bond, that's the functional group, and that would be an aldehyde. And once again, here we would have carbon, carbon, carbon. So all 3 of those together with the double bond there would be our ketone functional group. Questions on those classifications there? All right, then to lay up some names here, we're going to go straight across here. 1, 2, 3, 4 on that one. So that's going to be butanone. And again, you really don't need to give the number, because if it was here, it's the only place it could be. That would be 2. If you put it here, that would also be 2. If you numbered it, so it would be the same. So you don't really need the number here until you get to about 5 carbons. This is 1 and 2 carbons, which is based off of ethane, and it's an aldehyde. So that would be ethanal, Al. Again, do not need to give the number because this should always be at the end. Same thing here. We got 1, 2, 3, and 4, and there's multiple ways you could get the 4. You could go straight and up or straight and down to get the 4. So 4 of them there is going to be based off of butane. So that would be butanal, Al. Remember that this has to be carbon number 1 in this case, which means this has to be carbon 2. And that has to be carbon 3, where we have 2 methyl groups. So that's going to be a dimethyl butanal, and that's going to be a 3,3 dimethyl butanal, as you do need to give the location of each of the groups. Again, even if they are on the same carbon. Any questions on that one there? Lastly here, that's obviously a 6-member ring, which is based off of cyclohexane, and obviously it's a ketone, so we're going to go with cyclohexanone. Questions on any of those names? All right, so name these 2 and okay, let's take a look. So I see ketone group happening there, since it says name ketone, so that's good. That's 1, 2, 3, 4, 5, and 6 carbons. So that is going to be a hexanone, ONE, because it's ketone. We do need to give the location of that carbon oxygen double bond, which in this case, to give it the smallest number, would be 2 in this case. So 2 hexanone. Same thing here. We got a ketone. So got 1, 2, 3, and only 4, as that is chlorine, not a carbon. So that is 4, which is going to be butanone. And since this is going to be carbon number 2 in this case, that would be carbon number 1. That would be 3. That would be 4. That chlorine would be on carbon 4 there, a little 4-chlorobutanone. Yeah. Any questions on those there? Yeah. You don't have to, because really in this case, butanone is kind of will always be 2, because you need those 3 carbons. If you put it here, that would be 2 butanone. If you drew it here, that would be 2 butanone as well, because you want to give the smallest number. So you really don't get an actual sort of difference in terms of where that would be until you get to about 5 carbons, stuff like that. So, yeah. But it still is going to be obviously the lower number in terms of numbering for the chlorine in this case. So that's why we did go right to left in this case, to give that guy the lowest number. And because we locked in the numbering for that, we had to keep it for the chlorine. Okay. But let's first talk about how we prepare a aldehyde or a ketone. And they really are prepared from alcohols, and they are prepared from either a primary alcohol or a secondary alcohol. And it's through some reactions here we're going to talk about, which are oxidation reactions and reduction reactions. And when we talk about oxidation, it is losing electrons, it is gaining oxygen, it is losing hydrogen. Those are three different definitions of oxidation. Reduction is the opposite, gaining electrons, losing oxygen, are gaining hydrogen. So those are three different definitions of oxidation and reduction. And in organic chemistry, we oftentimes will look at the oxygen hydrogen sort of definitions as we're dealing with nonmetals in a lot of cases. So if we took a primary alcohol, there, we'll do something like this here, like this guy here. And once again, this is a primary alcohol because this carbon that has the OH group is attached to one other carbon, makes it a primary alcohol. And when we do an oxidation reaction of a primary alcohol, which is sometimes abbreviated by that, the definition that we're going to be looking at here is actually the loss of hydrogen. And what are they going to be? They're always the hydrogen that's attached to the oxygen and one of the hydrogens that's attached to the carbon that's attached to the oxygen. So it's always those two. So just like when we take out hydrogen, we have to put the bond back in. So what happens is when we oxidize that primary alcohol, everything stays the same except that you take out the two hydrogens. So the two hydrogens come out as this. And then everything else remains exactly the same here. So you could just copy exactly what's there. Obviously, you're taking out the two hydrogens. The problem, though, is if I leave it like that, my carbon there on the right is short a bond. So if you remember, every time we make a bond, right, we have to remove two hydrogens. And that's exactly what we just did here. So we talked about that with alkenes. Every time you kind of put a bond on, you take two hydrogens off, you put a triple bond on, take two more hydrogens off. So the double bond will always end up right here between the carbon and the oxygen. And that is going to make our aldehyde. So if you oxidize a primary alcohol, you remove two hydrogens, you throw a double bond in there between the carbon and the oxygen, and you will make your aldehyde group there. Any questions on that there? Now, aldehydes can actually be further oxidized one more time. So you could actually then decide, I would like to oxidize this guy one more time. And on the second time that you oxidize this guy, you're actually going to do this definition of oxidation, which is you're going to basically insert a oxygen. And where's the oxygen always going to go? It's going to go right there. So you're going to insert the oxygen basically right there, which means everything else is going to be the same. Absolutely nothing else changes. So we have an H, a C, an H, an H, a carbon oxygen double bond. And now here, I'll make it a different color. We're going to insert our oxygen. And then obviously we will still have our hydrogen that will be there as well. And our hydrogen. And that again is the oxygen that gets inserted. And this makes another type of organic molecule, which is known as a carboxylic acid. Any questions on that there? Now, in terms of our names here, just so you know, this is ethanol because it's an alcohol. This is ethanal because it's an aldehyde. And this guy, as you might be able to guess, is still based off of ethane. This is what is known as ethanoic acid, which is how you name a carboxylic acid. You put OIC acid at the end of it, and they're all basically based off of the same name there, which is all based off of ethane, basically, as you go through it. Any questions on that there? So to prepare an aldehyde, you basically take a primary alcohol, you oxidize it, and you will make an aldehyde. Now, if you took a secondary alcohol, like we'll do this, I think. I'll draw everything out, I think. We'll do this and that. So once again, this is a secondary alcohol because the carbon that has the OH group is attached to two other carbons. So that is a secondary alcohol. And if you put this through an oxidation, the same definition that the first guy did is going to happen here. We're going to lose H2. So we're going to be the H on the OH and the H on the carbon that's attached to it. Everything else becomes the same. So we're going to have our H2. And I'm going to, again, just copy exactly what's there. So I have an H, a C, an H. I'm not going to think about it. I'm just going to copy it. Yes. I clearly am going to get rid of the two H's that are in boxes because that comes off as H2. Everything else stays the same here. And just like before, because I removed two hydrogens, what's going to happen is I will always insert my double bond right there between the carbon and the oxygen. And that will make our ketone here. Yeah. And that is our ketone group, as we could see right here, 3 carbons in a row with our carbon oxygen double bond happening right there. Now, if you wanted to oxidize your ketone one more time, no reaction. The reason you have no reaction is, frankly, this guy right here has no hydrogen. And it's essential that it needs a hydrogen for it to work. And because it has no hydrogen, you cannot oxidize it any further. First off, any questions on those? By the way, if you have a tertiary alcohol, you cannot oxidize it either because it is missing the hydrogen as well. So again, not that one. So primary alcohol gets you your aldehyde. You could continue on with that aldehyde and oxidize it one more time to a carboxylic acid. A secondary alcohol, if you oxidize it, will get you a ketone, but you can't go any further than that. And in terms of the naming here, this would be 1, 2, 3. So this is 2-propanol. Oh, well. And this is, as we just talked about, 1, 2, 3. That is propanone, right? Now, these are all oxidation reactions where we're getting rid of hydrogens, and then on the top guy, obviously adding oxygen. If we wanted to do reduction reactions, you're just going backwards. So if we were heading in this direction, put it through a reduction, we're basically just going to put the hydrogens back on where they came off, and that will obviously make that into a single bond. And if you put the hydrogens back onto the carbon-oxygen double bond here, you would be going through a reduction reaction, which is basically the opposite of these reactions. So oxidation takes off the, puts them back on, and obviously rid of your double bond. Just like we talked about with the alkenes and the hydration reaction, hydrogenation reaction, basically adding 2 hydrogens, symmetrical addition to the double bond is where those hydrogens basically would end up. So why this is important is there are a couple of tests to help you identify whether or not you started with a aldehyde or you started with a ketone. Tests that you could run to figure these things out is, one is the Tollens test. And the Tollens test, sometimes referred to as the silver test. And basically what happens in this case is you take an aldehyde here, and our silver gets reduced, and our aldehyde gets oxidized. And in the process of doing so, the silver will actually turn to solid silver, and it looks like a mirror, which is why I sometimes refer to as the mirror test. But it is a positive test for a carboxylic acid that you will get here at the end. So if you and run the Tollens test, add some silver +1 ion in there, which is the Tollens reagent. The Tollens reagent will get oxidized. It will look like a mirror and become solid silver. And that will be a positive test that carboxylic acid also would be a positive test that you started with. And obviously an aldehyde and not a ketone if the test was positive. Another popular test, which I think is the one you guys do, which is the Benedict's test. And the Benedict's test use copper. And the same thing happens here. Copper +2 gets reduced to copper 1. And this guy gets oxidized. And once again, this is our aldehyde that will make our carboxylic acid, as we were just talking about. And what will happen here is the Benedict's reagent will go from like blue to a really gross looking orangey brownish type of color, reddish, I guess, ideally in a perfect situation. It will kind of look like this. I think there's a picture. There it is. So we'll kind of go from this and then obviously to that. That once again would tell you, and again, probably in yours it'll look a little bit more orangey, I imagine. But it's the same test I think you did when you had the dialysis bag the other week or something. And I think you did that in that experiment. And that's the same test that you would do. This again would be a positive one for, again, an aldehyde and not a ketone. So if you did either of these tests and it was negative, so you didn't see the silver happen, you didn't see it turn red or orange in your application for your lab, that would mean that you did not start with an aldehyde, but you started with a ketone, as the ketone would not give you a positive test for a Benedict's reagent. Any questions on that there? Okay. So as I mentioned before, the reduction reaction of aldehydes or ketones are basically the opposite of the oxidation reaction. And basically what happens is if we look at a aldehyde, we'll just do a very simple one here. And if we did the reduction reaction, which is really just a hydrogenation reaction, it is exactly the same as when we had, again, sort of the carbon-carbon double bond and we added hydrogen. What we do is we make this into a single bond, right? And then each of those guys get a hydrogen. The same thing works here with an aldehyde or ketone. When you add H2 to it, the only place where there is a double bond is between here. So that becomes a single bond, and that allows a hydrogen to go to both locations. So what would happen is we would redraw this exactly the same, CH3, CH, and we're going to make this a single bond. Now we have room for one hydrogen to go there and one hydrogen to go here, which will again give us our alcohol. And it works the same with both a aldehyde or a ketone. Basically, that double bond where the carbon oxygen is becomes a single bond. Each one of those guys gets a hydrogen, and it will take from a ketone or an aldehyde. And again, that's basically the opposite of the oxidation reaction we just talked about, which is the reduction reaction. And that's basically along the way. Any questions on that there? All right, we'll lay it up there, I think, for now.